Okay. It's really nice to see so many people come out on this really warm evening. I think the problems with air conditioning really helped because that's the only reason why I left my house today. So, but yeah, after that amazing talk by Yuri, this one now, okay. I'm going to tell you a little bit about radio astronomy and particularly the radio window to galaxies far, far away. So basically, you're focused more on the optical side of things, things that we can see with our own eyes, similar to that. But there's also a completely different window of wavelengths that paints a completely different picture of the universe at times. So that's what I'll try and focus on today, which is also very similar to it for my PhD. So it's good practice for me as well. So to start off, if I tell you this is a galaxy, you'd be very confused because this is nothing like the kind of galaxies that we've come to admire for the past few years, decades, from science fiction novels and stuff like that. But this is actually a radio galaxy. I know, is this fine?
You want to use this?
No, let's try it. So this is a picture of a galaxy at the radio wavelengths, and what you're seeing here is these two beautiful jets coming out from the central part, expanding into these beautiful big radio lobes. And to compare this image to what we used to with the optical wavelengths, this is an object that we all love and admire and can accept that this is a galaxy. So this is actually from the Hubble Space Telescope. It just shows the light from the stars and the gas around it, the optical wavelengths, very normal. But when you point a radio telescope in the exact same location, you see something completely different, which is very close to the image that I showed you earlier. And this is the radio emission that comes out through radio telescopes, which is not coming from the same location as the stars in the galaxy, but very, very far away where the galaxy is. And it's also, to put it into scale, the scale of the radio emission is much larger as well, compared to just the optical light coming from the galaxy. So that's what makes radio astronomy very interesting, because it proves a very different part of the universe, or it's the same object, but a very different physical process that powers this. So I thought I'd paint a little historic picture of radio galaxies and where all our information and where the field currently is, where it all comes from. And I think the best place to start would be in the 1950s, just after the war, when a lot of the radio equipment that was used during the war to detect enemy planes was finally available for researchers to do some exciting science. And one of these telescopes was in Cambridge, and they all just started pointing it towards the sky and just surveying the sky at radio wavelengths to see what comes out. And these Cambridge surveys in the 50s and 60s really pioneered the field of radio astronomy, especially astronomy at a large scale in the sky. And what came out from these radio telescopes was very interesting. These are some of the images that were detected, these sources in the radio were detected from the Cambridge catalogue, which you can see from the names. They're called 3C, which comes from the third Cambridge catalogue. And all the numbers are basically just the entries in that catalogue, and these names became names of galaxies. So CR7 wasn't there at that time, otherwise it could have probably been more inventive, but this is what sort of set the tone for radio galaxy names. And you can see immediately that there's all kinds of things happening. There's these fuzzy blobs, these little jets that are along the same line, and something in the middle, which is very bright, and yeah, all kinds of shapes and sizes. But what astronomers did next was, once you have the radio detection and the radio position, they pointed the optical telescopes in that direction to see what actually is happening in the optical wavelengths. And what they discovered was these galaxies look pretty normal in the optical, but when you look in the radio, they have something weird going on. So this was the first real statistical sample of these radio galaxies that people discovered. So not all galaxies shine in the radio. There's only a few very special and rare galaxies that have radio emission associated with them. And with these follow-up at optical wavelengths, they basically could come up with some basic properties of radio galaxies, which was first that a galaxy that also shines in the radio is more likely to be red and elliptical and spherical, as opposed to a blue galaxy, which has beautiful spiral arms, like our own Milky Way. So this was something which was very common with radio galaxies. They were red and they were spherical. The other thing people noticed that a lot of these radio galaxies, when looked at in the optical, were surrounded by many other galaxies around them. This was a very common feature as well. So they immediately started associating these radio galaxies with these clusters of galaxies, or galaxy clusters as we call them now. And the other unique property was that sometimes the radio emission was coming from a merger of two or more galaxies, forming an even more massive galaxy. This is a very rare event in the universe, which could be traced by radio emission. So this was all these sort of exotic phenomena happening, which were revealed by radio, and you could start developing theories and models as to how this happens and how this works. Well, there were a few sources that puzzled people for a very long time, and this is one of the very famous sources that led to almost a 10-year debate about what this actually is. So this is 3C273, so it was initially selected using the Cambridge catalogue in the radio, and when they pointed the optical telescopes toward it, they found this little guy in the middle. And immediately it's pretty clear that it's not like any of the other galaxies that we saw before. It looks a lot like a star because it's very bright, it's very compact. But the trouble was that people didn't really expect stars to be very bright at radio wavelengths, so we were very confused as to how this exotic star is actually producing all this radio emission. And the other problem was that if this was indeed a galaxy and not a star, it was almost 50 to 100 times brighter than all of the other galaxies that people found by following up radio emissions. So they had no idea what was going on, and they called it a quasi-stellar radio source, or a quasar for short. And then there was actually the Dutch astronomer Martin Schmidt, who was born in Groningen, but he worked and lived most of his life in the US. He actually published this groundbreaking paper in Nature, which is one of the top journals in all of natural sciences, calling it a star-like object with a large redshift. So this was very key, because a redshift is actually indicative of how far away a galaxy is. So CR7 was redshift 7. So it tells you, gives you an idea of the distance. So what exactly was this redshift? So here you can see that, as you already mentioned already, that hydrogen, helium, oxygen, carbon, they give these specific emission lines at specific wavelengths that astronomers can study and constrain what's going on. So you see here that there's a comparison spectrum with the H delta, H gamma, and H beta emission lines, which have these emissions where they're supposed to be. But when they took a spectrum of this galaxy, for this star-like object, they found that these three lines were all there, but they were just slightly shifted to the red. And that's what they called a redshift. And basically, a redshift translates into a distance which places the source really outside our own galaxy. So it cannot be a star with this redshift, it's just not possible. And by the calculations that they made, they discovered that the source ought to lie 3 billion light years away from us, which was absolutely groundbreaking at the time because nothing so far away had been discovered. And this is in the 1960s, so it was really revolutionary. But the problem was now that, as I already mentioned, that this object was 50 to 100 times brighter than all of the other galaxies. So all the stars in this galaxy would not be able to justify all the light that we were seeing from these. So it took another few years, a lot of debate, a lot of discussion, and astronomers could finally come up with a model that would actually explain this really bright nature of this galaxy, which is also very far away. And what they needed to do for this was to make the assumption that there must be a supermassive black hole in the center of this galaxy, which is orchestrating all of this extra emission that we see. And this was essentially the engine of this quasar. And they postulated that to have this energy, this supermassive black hole must be at least 1 million times more massive than our own sun, which is crazy. And what they essentially postulated was, due to the amazing gravity of this very massive object in the middle, it starts eating up things around it. That's what black holes do. That's what all these science fiction films tell you as well, which is true. If you put things around a black hole, it would be eaten up by the black hole. And especially if the black hole is so massive, its sphere of influence is also very large, so it starts eating up more and more of this material. And what happens when material starts falling into this black hole is that it really heats up and it launches these very collimated jets that actually go away from the galaxy. This is all very complicated theory, but essentially the picture is this: that when you pump a lot of material into a central part, some of it starts escaping from the top and the bottom. And this is essentially what is powering this quasar that we see. So the material that is falling into the black hole is generating so much energy that this little area of the black hole completely outshine the entire galaxy, just because of the very crazy exotic physics that is happening, which the theories had to be made to explain these things, so these were never used earlier. So just to demonstrate what actually happens, I have a little movie that I stole from the internet. In fact, everything on the internet. So here, there's a little black hole in the middle, and it's surrounded by this material which it's eating up. So it forms a disk around it, and it's all falling inside. So if I let this movie play for a little bit, you can see this material is swirling, and it's giving rise to these very powerful jets that are escaping the central areas. And to put this into scale, that little bit is the black hole, and all of these stars that you see are part of the galaxy that the black hole is in. So the conclusion is that that little supermassive, I mean, not little, but that's physically little supermassive black hole in the more bigger context of the entire galaxy can produce so much energy that you completely outshines everything around it. And this was truly exotic phenomenon that was completely revolutionary at the time, and as a result, Professor Martin Schmidt ended up on the cover of the Time magazine, where they called it "Exploring the Edge of the Universe," because it was so beautiful theory, and how we could discover such objects so far away, we could still see them to be as bright as they are. So this essentially sparked a new field where people were dealing with high energy phenomena in galaxies, and they were finding supermassive black holes almost everywhere. So this really changed the field. So now we come to the question of where are we today, just with the historic context. So just as an example, I don't think we've made much progress on the time in covers over the past few years. This is very interesting because it also shows how a few decades ago, like, scientists were the real heroes, and now we live in times when completely confirmed scientific theories are disregarded when it comes to policy making or economic decisions, and even like people just completely don't trust scientists anymore. So in that regard, I think we're really regressing. But thankfully, from the radio astronomy point of view, we made tons of progress over the past 40, 50 years. So going back to 3C273, it was confirmed to lie at a very, very large distance from us. And it was also confirmed to have a black hole which is 800 million times more massive than our own sun to actually power this. But over the next decades, quasars in these radio galaxies were discovered at increasingly large distances. And it was also understood that almost all the massive galaxies have these black holes in their centers, and they must have gone through the same active process to actually explain galaxy formation and galaxy evolution and really the regulation of galaxies. So this became part and parcel of our understanding of the cosmos. And just to put that into perspective, here's a little cartoon image of the history of the universe, where it starts with a big bang, and there's inflation, and then nothing happens for a long period of time, and then the first stars formed that Jordan talked about. These start to form into galaxies, and the galaxies grow, and the universe grows, and we end up where we are today in the Milky Way. So now, just over the last couple of years, a quasar was discovered 13 billion light years away. So to compare that with the 3 billion light years away that CC273 was, we're really, really pushing the edge of the universe to try and detect these really far away objects. And as Yuri bashed the galaxy that we discovered already, TGSS J1530 plus 10 was discovered by our team here in Leiden. And this is a radio bright galaxy which is 12.7 billion light years away as well. So because of these theories, we're actually able to find these very exotic, very distant, very exciting radio sources really, really far away towards the edge of what we can observe these days. And it's really changing the field. And going into the future, there's better and better radio telescopes coming online. And here are just a few examples of the state-of-the-art radio telescopes that we have today, with the GMRT in India and the Very Large Array in the USA. And of course, our friendly neighborhood LOFAR, which is based in the Netherlands, which is a very revolutionary radio telescope in its own right. And in the future, we have the Square Kilometer Array, which is essentially a radio telescope on steroids. It's going to be built in 2 countries and it's going to operate at the same time. So that's going to be in the southern hemisphere in Australia and South Africa. So the future looks bright. If you're a radio astronomer, and it just gets better and better. So thanks a lot.